I'll talk a little bit about these quantum sets of colored graph approach and contextuality. This is a joint work with Lina Vandré. Actually, this is results from her master. And today is important not only for us to be here, but also because it's Barbara's half an hour after the meeting can be used for celebrating as we would do if we were at Prague. Okay, so now the talk. I will base my talk on one of the ways of talking about contextuality, the so-called graph approach that started from Adan Cabello, Simone Severini, and Andreas Winter, that can be resumed as these expressions. Let's say that we have a graph, in this case, the pentagon, the first example of exclusivity, and we add probabilities given for the events represented by those exclusivities. Under a non-contextuality hypothesis, we cannot have more than 2 for the pentagon. Under quantum theory, we can go up to square root of 5, and under more general concerns only regarding exclusivity, we can go up to 5/2. Actually, it's more general. If we have a general graph of exclusivity, this sum is bounded by, is upper bounded by 3 different graph invariants, the so-called independence number, the fractional packing number for the last one, and the quantum theory concerns the lowest number. Okay, so just a few review of graph approach, of CSW graph approach. We can start from what we call the exclusivity graph of a scenario. And for the simplest examples, we have this first graph for the so-called CHSH scenario that all of us are used to, and the KCBS scenario of the pentagon. And you see that we have black dots in some of the vertices that is related to inequalities, to specific inequalities. So here we will have, and all those events are labeled in the sense of measurements and outcomes. So here we have the context of measuring 0 and 1. Analogous, here we have the context of measuring 0 and 1. All of them dichotomic measurements, and all the results appear in each context here. And then changing from one context to another, the measurement 1 belongs to both contexts, 0 and 1, and 1 and 2. And this is things that you are used to, I believe. If not, just we can use the discussion for this. But if we consider just the black dots here, the black vertices, then we have the inequalities. So first example, KCBS inequality, and another example, the graph of the CHSH inequality given by those black guys. Of course, we could have other CHSH inequalities coming from the same scenario, all of them equivalent, but with different choices of induced subgraphs here. Okay, and this CHSH inequality can be rewritten or redrawn as this pizza graph here that has the same 8 events that were drawn before, but now in this different representation, this different viewing. And the important part of the graph approach is that we can recall the inequality from it. We have the sum of the probabilities of each of those events, and we can understand the upper bound as the independence number, as the largest, the cardinality of the largest set of vertices that we can choose here. And in this example, 3. This, as I already said, is the independence number of this graph. And essentially, this is the non-contextual bound for such an inequality. And we are simply using our classical way of thinking to derive this notion, and this is consistent with classical probability theory, that now we can forget about the labelings that were there and say, okay, we have the same thing under those same concerns. However, we can change our concerns now. We can say, no, I'll not consider those ideas, but I'll use the idea of orthogonal representations. We can start assigning from each vertex, for each vertex, one vector, some vector space. Every vector I will consider in this talk must be unitary vectors, must be vectors with norm 1. And the orthogonality will be demanded in this sense that whenever we have an edge connecting two vertices, then the vectors, the corresponding vectors, must be orthogonal to each other. We choose another unitary vector, another vector of norm 1 psi, called the handle, and we simply make this square of the inner product of them, the modulus square of the inner product. Physicists can recognize here Born's rule, but people from computational science, for example, will simply recognize Love's theta number. And this is the essential connection that was made in CSW approach to say, okay, those two things essentially are the same thing coming from different places, from different sets. And this is a quantum bound for the graph, not necessarily from the scenario that we have started, but from the graph, just the exclusivities are being considered here. And we are using here what can be considered as a quantum reasoning, as one example of generalized probability theory, as we already heard. Okay, I'll just make a small amendment to it in order to introduce the colored graphs, that we could make all the discussion, instead of using vectors, using projectors. If you want, you can use one-dimensional projectors. This is enough, but not necessarily. We can use any rank projectors. So for each vector, for each vertex, we associate one projector with orthogonality, meaning this condition here, and everything else goes smoothly, okay? Okay, so back to CHSH inequality graph. We have this set of events that we selected from the previous example. But if we start from here, where are Alice and Bob? Of course, we can consider that those players appear, but even in the way we label here as 0, 1, 2, 3, this has nothing to do immediately with Alice and Bob. But of course, the compatibility graph allows for it if we consider that those pairs must be compatible in a sense that we can discuss in the discussion part. This was my comment in the morning, but I will keep it to the end. And we can consider the compatibility graph in this sense. And here we see a bipartite graph, essentially. I already organized the even part here, the odd part here. And this is where Alice and Bob are allowed by this structure. However, take a look at this vertex here. I will change only those labels, and you can see that another compatibility graph can be considered. We can have another Bell labeling. We can have another Bell scenario that also allows for an inequality like this. So, or a graph like this, at least. Again, that's a related inequality. Okay, so how can we demand Alice and Bob in this discussion? This is the central issue that those guys here were concerned with some years ago and introduced what we call the colored graph approach. So the CHSH colored graph is essentially the same graph as before, but with those colored edges that are essentially concerned with which player makes the orthogonality, which player makes the exclusivity. And here we change the notation to 0 and 1 for Alice, 0 and 1 for Bob instead of 0, 1, 2, 3. In a sense, it's just a change of notation, but with this important meaning that now we do have two different players. We do have Alice and Bob, and here we have this colored graph that is, the edges are the union, this union with no intersection. I forgot the usual name for this, but the union with no intersection of GA and GB. So here's the set of edges. Now GA is this graph with the same vertices and the edges given by the red ones, while GB is the graph given by the same vertices, numbered 1 to 8, and the blue edges here. And this square union here is to say that we can have double edges. That's exactly what happened in the specific CHSH example. And this is what's shown here. And our claim, or our original claim, is that everything of the inequality is in this graph. We do not need to write it here anymore, because this graph already has these factors here that say that we need one measurement 0 and another measurement 1. Each piece of them, each piece of the color red graph needs one different question, and two different answers is enough to organize these specific exclusivities. Okay, but my intention is not to introduce the colored graph approach. You can take a look at the colloquium if you want, if you have never seen. So let us move on to say that orthogonal projective representation must be adapted here, and we can introduce the orthogonal projective representation that are necessary or that are suitable for colored graphs. So what's this? We introduce the tensor product to say, okay, for each vertex, now we have one representation, one projector for part A, another projector for part B. And the orthogonalities must come depending if they are connected in the X part. So X here means A or B. If they are connected in the A graph, you need orthogonal projectors in A part. The same for B. If they are connected in B part, you need orthogonal projectors for B part. Again, you need a handle that lives in the vector space that's used here, the tensor product of the two vector spaces, one for A, one for B. And again, the probabilities will come from something like Born's rule. Okay, so just the generalization of the original idea. And we can introduce this new invariant that is the two-colored lowest number. Two-color because we are dealing with a two-color graph. Of course, if we had more parts, we would need more colors, and we would have the analog for the projective representation and for the colored lowest number. Okay, but you are doing the same as before. It's more important to remember that we have a sup here instead of a maximum. And the important consequence is that due to the tensor product, we do not have a semi-definite program anymore. We actually have a hierarchy of semi-definite programs. And just like in Navasco-Spironi-Wassim hierarchy. And this gives to us practically, whenever you stop in one level, you only have an upper bound for this number. And we can also obtain lower bounds by showing specific examples of representations. And of course, if we make this gap small enough, we have a good approximation to this number. Okay, so one thing that we were happy in that time is that we understood better the pentagonal Bell inequalities. So this is one of the pentagonal Bell inequalities that really appear from these 5 vertex here, numbered 1 to 5. We can see the double edge here comes here, and we can understand everything in this case. Again, another family, the 2 other cases of Bell pentagonal inequalities can be understood as the same colored graph and only a choice of scenario, of Bell scenario, to embed these exclusivity relations. So this is related to this number 2 here, that is whether we consider a third measurement in red part with only one outcome, or we forget about it and consider just marginals here. Okay, this is described in the paper that introduced the colored graph approach. But just refreshing what we have seen so far, that's just to remind, in a sense, old stuff. CSW, Cabello, Severino, Winter, only sees exclusivities. In the colored graph, we can characterize which part sees each exclusivity. And more restrictions mean lower upper bounds, just as it happens in the case of the pentagon, where we have this pentagon with double edge here, with a smaller 2-colored lowest number than the other pentagon with no double, and this is strictly smaller than the lowest number of the pentagon itself, that's square root of 5. But for the CHSH case, we had the surprise that those 2 numbers are equal, despite the fact that we have the restrictions given by colors and even the restrictions given by the double edges here. So this was something that surprised at least me a lot from the original moment. And we need to understand a little bit better that, okay, the number can be equal, but colored or graph approach to contextuality and colored graph approach to contextuality is not only about numbers. It can be described also regarding the sets of correlations, the behaviors or the models that we can obtain. So given a graph, I'm just recalling here what a representation or orthogonal representation mean, and we can collect all those guys for each given representation, orthogonal representation and handle, and build this beautiful body, this beautiful convex body, as we can show. That's the theta body of the graph G. So we are simply considering this collection of vectors of probability, vectors which are made from probabilities calculated in this way, labeled by the graph, the vertices of the graph. Okay. And analogous, if we go to the colored version, if we have a, from now on I will use this calligraphic G for colored graphs. If we have a bicolor graph in this case, we can again use the bicolor representation, the tensor product representation, and also make the same idea and define this colored theta body of the colored graph G. And if we simply consider that the vertices are the same, that we are simply considered G as a shadow of this colored G, it's immediate that we have this structure, that one is a subset of the other, but not necessarily a proper subset. It could in principle be the same, since each representation here can be, we can simply ignore the tensor product and say, okay, this is also a representation here. So it's natural that each behavior that you can have here is also a behavior there. And the question that we made is, okay, it's not the question yet. So those are also called the quantum sets, in the sense that we can use those representations to understand quantum realizations of those behaviors. So this is the quantum set of the graph G. This is the quantum set of the colored graph G. And we have this structure of one is inside the other. For the pentagons, the same happened, but there we already know that this structure is strict because different theta number mean this, that you already have unattainable values for some of them. But here we still had the question, can they be equal? It can happen that every behavior that we can obtain as a NC inequality, CHSH, can also be obtained as a Bell inequality, as considering the parts taking part of the description. And this is when Lina Vandré entered in this discussion. So she took the idea of, okay, let us solve it. Let us find at least one point, one behavior that is in one set and not in the other. So what is the central idea for working with this? To recognize, and this is already in the graph approach spirit, that we do not have only one inequality. For each weighted graph, the same structure, but different weights can, and a weight here is simply a weight vector that for each vertex associate one non-negative number. And for each weight vector, we have a new inequality that can be seen from this inner product of the weight vector and the probability behavior, the probability vector that comes from the graph, from each realization. And this thing will have a classical bound, that's the so-called independence number, the weighted independence number of the graph G. And again, for each weight vector that we choose, we are walking in a different direction in both bodies, in the theta body of the graph G or the colored theta body of the colored graph G, according to which of them we use here. Okay, and this is what will be used as a strategy to solve the problem using this family of graphs. So here above you see the original CHSH Bell graph, so the two colored Bell graph that you have already seen there. And here from each level, we simply remove one edge. So in this level here, you can see that this guy here is only orange, so no blue here anymore. Of course, we could have removed blue, but this is symmetry. This is symmetric. So this is the representation of the graphs up to symmetries, up to automorphisms of colored graphs. And changing one color to the other is one of those symmetries. And here you can remove one more and you have 5 different options of what to remove, keeping always the same shadow. So we cannot remove any edge that's already a simple edge. We are always removing one of the edges of some double edge, okay? And you can complete this beautiful figure here. And just for you to mentalize, to analyze now, the important ones for the rest of the talk will be this one here that Lina denoted G441111. This notation says that the orange part has 2 4 cycles, while the blue part has those 4 1 1 1. It's just one edge here, another edge here, another edge here, another edge here. The other important guy will be this one, G3333. So no cycles anymore, but 3 edges in blue, 3 edges in orange, 3 edges in orange, 3 in blue, 3 in blue. And this is what's represented here.
Marcelo, you still have 3 minutes left.
About finished, thank you. And here, also it's important to consider this chain of subgraphs. So above this guy here, oops, sorry. Above this guy here, we have this other graph that I do not need to read the name, but just see that we have this double here. So one edge was introduced from here to here, another edge introduced to here, another edge here up to there. And we see that this chain naturally has the quantum sets also chained in the opposite way, since introducing edges in principle include restrictions, so make this quantum set smaller. And this is one of her results that clearly show that they are not equal. So what's being doing here? We are using one parameter, epsilon, to change the weight. And this weight starts from just 1/8 for each one that's here. That's why we are calling CHSH. While if we take a look here in the value 1 for this epsilon, this means that only the 5 vertices of a pentagonal inequality are being considered. So this is, and what we are doing here is to vary from one to the other to make a change in the weight vector from one to the other. And in this region here, you can see that those two graphs that I pointed out to you have different upper bounds. Okay, the upper and lower bound essentially coincide in this visualization here, and you see that really the numbers are very good. So they are really very close. The fourth digital can enter here. And so here in this region, we have guys that have behaviors that cannot be in the CHSH part, but can be in G3333. And above here, they are not even in G3333, but are in G441111. Okay, another beautiful thing, the chain that I already stressed to you. Here you see for each of them the upper bound, and you can see differences, but curiously some of them are not clearly different. So it's not impossible that some edge removing do not affect the color theta, at least in these directions. This is part of the questions that I raised in the end. So to wrap up, we showed that the quantum set of the shadow of CHSH is strictly larger than the quantum set of the original CHSH, that there are many colored graphs in between CHSH and its shadow. We don't know yet if there are as many different quantum sets or not, if some quantum sets can coincide for different colored graphs. This is an open question. And if quantum, okay, this is exactly what I have already said. If they can coincide, the other alternative to as many as there. And clearly open questions, if there is some graph characterization of when can we remove one edge without changing this complete set, this will be somehow surprising, or at least as happens for CHSH, without changing the lowest number, the colored lowest number for one weight choice. So this can be another thing to be understood. One other mystery that we have seen for that specific weight choice, that the ordering in between those two guys appear. I suppose that changing the weight vector, we could see the opposite ordering, but we could not find to the moment any other weight vector that changed the order. So to the moment, it's not impossible that these quantum sets, so this key is simply the quantum set of the graph, corresponding graph, this can be a subset, a proper subset of that other guy without any clear reason why this happens. So it's something that we also would like to understand. And using Sivosius' term, we also have to prepare the quasi-empirical version of those results, since we are showing that the non-contextuality set is larger than the Bell set. We really want to take one of those points and say, here is the experiment that should be performed to make it clear. And it's related also to the comments that I will do during the discussion time. So thank you all, especially organizers,